Think Celsius, because Charles' law is the law that relates gas volume to temperature. As boils is to bubbles, Charles is to Celsius. Charles' law states that assuming a constant pressure, as temperature decreases, the volume of gas decreases. Conversely, as the temperature increases, the volume of gas increases.
This is more to do with aircraft performance than with physiology, as we rarely see dramatic changes in the temperature of the gases around us. You see the effect of this all the time, though, when you're using oxygen and the bottle becomes very cold.
That's the gas inside the bottle drawing heat through the metal of the bottle as the gas expands. When a rocket like the Saturn V lifts off, it burns 18,000 kilograms of fuel per second, and the falling pressure in the fuel tanks causes condensation to form and then freeze on the sides of the rocket. It's this ice that we see falling off the sides when the rocket lifts off.
Charles's law, then, can be written as volume is proportional to temperature. As we said in the last video, this means that the two values change in lockstep together. We can also write it as an equation by adding a constant k.
The role of the constant k is just to reflect the specific properties of each different gas. Hydrogen doesn't expand at the same rate as argon, for example, so the two will have a different value of k. We often use Charles's law to compare the before and after case when we change the volume or temperature of a gas. We can do this by writing an equation that has the first case denoted by the subscript 1 on the left, and the second case denoted by subscript 2 on the right. If we make any change to the left side, for example increasing the temperature, then in order for the two cases to remain equal, we have to increase the volume on the right side. So, just like we said earlier, assuming a constant pressure, as temperature decreases, the volume of the gas decreases. And as temperature increases, the volume of the gas increases.
Although we use Celsius as a mnemonic to remember Charles's law, we actually use the Kelvin scale when we work with gas laws. The good news is that converting temperatures between Celsius and Kelvin uses a 1-to-1 ratio. This is not the case if we start with Fahrenheit. Really, the only difference between the Celsius scale and the Kelvin scale is where they start. In the Celsius scale, 0 degrees is the temperature at which pure water freezes, and in the Kelvin scale, 0 degrees refers to absolute zero, which is the temperature at which particles of matter are practically motionless. So because 0 Kelvin is about negative 273 degrees Celsius, the conversion between the two amounts to simply adding 273 to any temperature expressed in degrees Celsius.
Gay-Lussac's law is closely related to Charles' law. Gay-Lussacs law assumes a constant volume and only the pressure and the temperature vary. As you might expect, as the pressure increases, so does the temperature, and vice versa. Similar to the way we wrote Charles' law, we can write Gay-Lussac's law as an equation with the constant k to reflect the specific properties of each gas. And again, if we write out the equation representing the before and after cases, we see that if we change the value on the left, increase the pressure for example, we'll have to change a value on the right, increase the temperature, to keep the equation balanced.
Neither of these laws have any real significance physiologically, except that at altitude the pressure is progressively lower, and the air temperature falls correspondingly,
making you and your patients cold.
However, the effects on aircraft are significantly more important. If you're flying, you will hear about the concept of density altitude. Density is proportional to air pressure. In an open system like our atmosphere, increasing the volume occupied by a certain amount of air causes the density of the air to decrease.
We expect that as we fly higher in the atmosphere, the density of the air decreases. However, because we also now know that the density of air changes with temperature, we have to have a way to incorporate the effect of temperature when we try to predict the density of the air at any given altitude. Density altitude is simply a way of expressing the air density in a way that incorporates the changes in air temperature, and to a lesser degree humidity, into the altitude number so that it's easy to understand and relate to.
Density altitude gives us not the actual altitude, but the effective altitude. Saying the density altitude is 13,000 feet is like saying, even though we're actually at 9,000 feet, because the temperature is 40 degrees Celsius, or 104 Fahrenheit, the air pressure is the same as it would be if we were flying at 13,000 feet on a normal day.
This is vitally important because the density of air directly affects the efficiency of wings, both fixed and rotary. It also affects the capacity of the engine to produce power because the engine is dependent on the oxygen in the air, and less air per unit of volume means less oxygen. Take the case of a helicopter launching on a very hot day. The engine will produce less power and still have to attain a higher rotation speed in order to produce sufficient lift. The aircraft will climb more slowly and ultimately have a lower lift capacity. Similarly, a fixed-wing airplane will have to attain higher speed to lift off and need a longer takeoff to do so.